everybody. I'm Daniel, and together with my colleagues, I'm going to show you how we can generate correct page tables for the Barrelfish operating system from a hardware model with formal semantics. To be able to correctly manage a platform, the operating system, we use Barrelfish as an example here, needs to know where resources such as DRAM and devices are. In a modern heterogeneous system, the addresses at which the kernel sees these resources can differ depending on the core the kernel is running on. You can see an illustration of this in the diagram. Each core has a private UART and the DRAM appears in a different region of the address space. So depending on whether it's running on core 0 or 1, our kernel here needs different page tables. Current systems use a plethora of mostly ad hoc mechanisms to specify these page tables for components like a bootloader or a kernel. All of these mechanisms fragment and duplicate topology information and leave it to the programmer to get all the views right and keep them consistent. In the remainder of the talk, we will show you that there is a better way. If we describe the platform using a suitable hardware model with formal semantics, we can generate data structures such as page tables and memory maps from a single source of truth.
We base our model and language upon the decoding net. This is already published work, and the decoding net encodes the memory topology in a directed graph. Unlike existing approaches, such as device trees, it makes no assumptions about the observers in the memory system, and is fully formalized in Isabelle Hall. We call the language to describe decoding nets Sokai, and we use it to express real complex memory systems. In this talk, we are showing you a demo in a simulator in which we reconfigure the memory mapping. So how do we use this decoding net to generate page tables? We want to be able to access these gray accepting areas and also make the operating system aware of their location. In our example, we see 3 accepting regions, 2 private UARTs and a common DRAM. We generate the page table between 2 nodes. In this example, between kernel 0 and core 0. We use the direct translations between those to input the desired mapping. To get the necessary page table entries, we also have to know whether the region ends up at a device, in which case it has to be mapped uncached. We do this by reverse translating accepting regions into the observer node, while keeping track of any destination properties. The UART is reverse translated into core 0, from where it is reverse translated into kernel 0. We repeat the same process with the DRAM. We also repeat the same process with UART 1, but since it never ends up in kernel 0, we do not show it here. From this set, we have to do a one-step forward translate to understand which page table entries have to be generated. These entries are then fed into the backend of the page table generator, which creates a relocatable object file containing the page table as well as some meta information. This object file is then used in the bootloader and in the operating system initialization. Reto will show you now a demo how this works in practice.
In this part of the evaluation, we again start with a platform description in Sokai. However, we now generate 2 things. First, the Barrelfish operating system image with generated platform-specific low-level systems code. And secondly, the platform description file that specifies the simulator configuration. Thus, the operating system image and the platform are generated from the very same description file. Then we change the Sokai description and regenerate the platform and the operating system image. But let's dive into a demo. We are now looking at a Sokai file that describes the simulated platform. First, we have module declarations that describe how the various hardware components interact with the memory subsystem. For example, which memory region they accept. And you see here 2 examples of the UART controller as well as a DRAM device. A special module is indeed the ARM Cortex A57 processor. This module not only defines which type of processor we want to instantiate, but also specifies the desired virtual to physical address translation that needs to be set up by the generated page table. For example, the boot driver will obtain an identity mapping of the entire memory range. Next, we have the platform module. The platform module then instantiates the modules that we've defined above and defines how they are connected. For example, the ARM Cortex A57 will have a connection to its local cache coherence controller. A special type of connection are the bus decoders. Bus decoders define the local physical address space of the processors and at which addresses the local resources will appear on the simulated platform. On the left-hand side here, you see the output of cluster 0, and on the right-hand side, you see the output of cluster 1. So you see now Barrelfish is booting, and while this is happening, we are now going back to see what files have been generated. First, we have the Prolog file. The Prolog file is an executable version of the decoding net of that simulated platform. You see the different modules and its instantiations are being asserted and added to the knowledge base of Barrelfish that is then being used in the build process as well as at runtime. Secondly, we have the page table that's being generated. The page table is basically one big array of page table entries, and we also support multi-level page tables. Next, we also include different arrays corresponding to the device mappings as well as memory regions with its local physical as well as local virtual address as corresponding to the generated mappings of the page table. Okay, we actually see that the core boot driver is now loading the page tables as well as the different CPU drivers and boot drivers for cluster 1, and that on the right hand side the cluster 1 is being booted. Now let's try and change something. We go back to the socket description and change the memory layout of the two processors. Let's just set the address ranges on which the DRAM resources appear to some different value, and we do that for both of the clusters. And now let's just regenerate the simulated platform. Okay, so the new simulator is built and we can try and run Barrelfish again on the simulated platform. Now we do execute the same thing and we'll see that indeed we now have a mismatch between the operating system image as well as the memory map of the simulated platform. We actually see that the boot attempt now ended up in a panic as the boot driver attempted to access memory that is now at a different address. Now let's go and rebuild the OS image again. And we can run the simulator again, and now we see that Barrelfish now copies the address, the image to the new address, to the right address, and the boot process continues. And with that, I'm going back to the presentation. In this talk, we've shown you a better approach to deal with the complexity of modern hardware. We leverage Sockeye and the decoding net to obtain a more faithful model of the hardware platform. We have built a toolchain that generates low-level systems code such as page tables from the model and integrated it into the Barrelfish OS. Lastly, we've shown that this approach indeed works on a variety of real and simulated platforms. Sockeye is open source and available on GitHub. We highly recommend you checking it out. Thank you.